Okay, great. Welcome everybody. It's a pleasure to be participating here in this school. I have to say it's the first time I'm giving a course to physicists about philosophy. I have done physics to philosophers, philosophers to philosophers, physics to physicists, and this is the last that I have to face. So I encourage you to ask questions and comment on whatever point you might feel it's not quite clear. Also, after the course today, if you want to send me an email, maybe asking me to repeat something, I love to do it the following days. So yeah, so the organizers asked me to do a course on philosophy of relativity. And the question, of course, was what is relativity here, and the word relativity, right? Because we are here in a gravitational school, so one expects me to talk about probably general relativity and maybe some part special relativity. But of course, the notion of relativity is a wider concept, and as we will see, it involves basically all the space-time theories, starting from Newton up to Einstein. So I will more or less use this word relativity, or the principle of relativity, more rigorous, to as a path to explain different both physics and philosophical concepts around both space-time, motion, and at the end of the day, when we finish the course, I want to try to answer the question: what makes general relativity so special? Okay. So I see some. Okay. So I have organized the course as follows. We have 3 days. So the first day, I will focus on explaining basic Newton mechanics, which most of you know for sure, but I will try to maybe explain it in a different way. Um, the following day, tomorrow, I have to, because of some personal issues, we have to change the schedule. So it'll be from 12 to 1 a.m., the Brazilian time. I will introduce some notions of special relativity and a bit of philosophical discussion of how we can discuss in more rigorosity the principle of relativity. And then the third day will be about general relativity, the equivalence principle, and if we can make sense of the principle of relativity in general relativity, what does it mean, and how general relativity relativizes something, and we will learn what this something means. So let me just first give some recommendations. I saw that yesterday there was a course that introduced some structure of differential geometry. So I will briefly introduce it myself during today, but I will assume some basic knowledge of manifolds, tensor fields, connections, etc. So basically the language of GR. So of course there are many physics books. For me, the best book to really get a compact description of this language is Wald's book. But I will sometimes briefly discuss also Bergsman's book on relativity, and also Malaman's book on topics of foundations of GR. From the philosophical side, I will do a mixture between some more philosophy books, which do not have so much equations, for example, Understanding Space-Time, and more mathematical, philosophical involved books, which is basically Relativity and Geometry by Torretti, and Foundations of Space-Time Theories by Friedman. I recommend you to have a look at these books if you can find them, depending on your taste. If you prefer philosophical discussions with more text, then I recommend Desai's book. If you don't feel comfortable with too much text and you enjoy more good equations and also philosophical discussions, I would recommend you either Torretti's book or Friedman's book. Okay, so Now, the big question is why should we care about discussing these issues that I'm going to discuss the next following days? So this is a school about physics, and you have courses of different techniques and different consequences of general relativity applied to different physical systems. And of course, one has a lot of interesting questions and discussions about it, but of course, it assumes already the theory of general relativity. So basically, you are given a precise description of how general relativity works, and you just develop techniques in order to understand physical consequences of the theory. There is somebody with the mic open. Could you please close it? Yeah. So why should we then care about asking us about foundational principles of general relativity? Why go to the building blocks of the theory? Well, because basically physics has told us to do so, in my opinion. We know that gravity seems to behave quite differently from the rest of interactions. We have built a completely different language in terms of quantum fields to understand electromagnetic and weak and strong interactions quite successfully. While gravity has left aside because we are not able to describe these interactions at the same level as we do with the other interactions. When we go to the description of gravity that works, general relativity, we have to assume, accept the fact that the laws of nature tells us that gravity is just encrusted in the structure of spacetime. We cannot just discriminate between gravity on one hand and motion of spacetime on another. Okay, this is the core meaning of the equivalence principle that we will learn more about on Thursday. But at the same time, we know that gravity and matter interact, and they interact in a manner that is described by the Einstein's equations, where we have the left-hand side is the structure of geometry, and if we can use this word, the structure of what introduces the way we define space-time with a given curvature and a given metric. And on the right-hand side, we have the stress energy tensor. Now, the stress energy tensor, we introduce there all the kinds of matter that we know in the universe. And the problem here is that we know, as I said, how to describe matter, where here matter, we can assume that it's just given by some fields that interacts via electromagnetic, weak or strong interactions. And of course, we know that the stress energy tensor is way more complex than in the classical analog. In the case of quantum fields, when we talk about the stress energy tensor in a more mathematical way, we are not talking about a classical tensor field, but we are talking actually about operator value distribution. So that makes it completely different, the right-hand side from the left-hand side. And so actually Einstein thought about this way before we actually really constructed the full quantum field theory of matter. And he says, general relativity is sufficient as far as we know for the representation of experiences of celestial mechanics, right? So classical gravity. But it's similar to a building, one wing of which is made of fine marble, the left side of the equation, but the other wing of which is built of low-grade wood, right side of the equation. The phenomenological representation of matter is in fact only a crude substitute for a representation which would do justice to all known properties of matter. So what does Einstein mean by this? Actually, if one reads this paper that I put there by Lemkool in 2018, usually people assume that what is meant here by Einstein is that we don't know exactly, the stress energy tensor is a very chaotic thing that we don't know how to build. And then the part of geometry is beautiful and elegant. But he really didn't mean that at all. What he meant by this is saying that the stress energy tensor, which should inform us about how matter behaves, doesn't make justice to it, because matter is quantum, and Einstein knew that for sure, because he himself worked in quantum mechanics for a long time. He knew about the different properties of discrete energy, for example, that matter can have. And he realized that assuming a classical stress energy tensor to incorporate the information of matter would not be enough. And actually, for him, it was a not so a successful theory, GR, in the sense that it didn't incorporate the properties of matter in a unified way as the geometry of space-time. So what I mean then by this is that GR, or gravity, forces us to really understand what are the principles that construct this theory, because in some way it is different from just the ordinary matter, but exactly why and it is different and in which sense it is different is what is still unknown. There's okay. So then the question is, what exactly makes gravity from the point of view of general relativity so special? And what has it to do with the principle of relativity? Because obviously general relativity has the word relativity, and it is not, of course, the names do not mean too much in physics, but here there is some principle of relativity, and we see that historically Einstein really believed in the principle of relativity, both for special theory of relativity and also for GR. But what we want to understand is how exactly this principle of relativity takes place. How can we define it in a rigorous way, and if it means something for general relativity. So just to briefly introduce the topic here, Galileo says, "He who undertakes to deal with questions natural science without the help of geometry is attempting the unfeasible." Also, Penrose says, "I do not believe that a real understanding of the nature of elementary particles can ever be achieved without a simultaneous deeper understanding of the nature of spacetime itself." So here we see completely different centuries, but at the same time, the same point of view, right? That even though we try to escape from it, we still have to face the fact that we have some underlying spacetime structure, some geometry, and now we know on top of it that gravity is encrusted in this kind of feature that there is no way of putting aside. So also for Einstein, general relativity takes from space and time the last remnant of physical objectivity. So Einstein really tried to use the principle of relativity to avoid talking about space and time. For him, the whole idea of general relativity, at least at the beginning, was to dissolve any privileged motion, including both inertial or accelerated motions, so that we really don't require to define the laws in terms of a given motion, right? So at least that's what he tried to do at the beginning. We will see if this really was achieved, or if we still, even after GR, have to talk about privileged motion or absolute motion in this theory. Also, something I want to maybe discuss, because I think it's not so known, is the formulation of GR, especially after the 60s, has been mostly developed in geometrical terms. Now, mathematically, this is a brilliant language, because I will use it during this course, and we can understand many features thanks to it, talk about metrics and talk about affine connections and so on. But there has also been an interpretation in terms of physical geometry, right? When we usually give a talk to even like um, uh, students, for example, we always introduce GR as saying, no, the gravity is really the curvature of space-time, right? And that's what Einstein taught us. Well, I will try to reject this claim, both because Einstein never really tried to teach us that, even though we interpreted it that way. And we will see this is also quite arbitrary, because we will see that other theories, like Newton's theory, for example, can be expressed in a very analog way as curvature of spacetime. So we will have to reevaluate what does it mean for general relativity to be geometric. Okay, so how I approach this course is twofold. So two things that we will need to learn is first, we want to know why GR is so special. Then the question is, how does GR compare to other theories? And in particular to the other two known theories of space and time, which is special relativity and Newton's mechanic, right? So of course, if we want to compare these three theories, we need to write them in a similar language, right? So I will spend some time doing this. And then the other question is how to define the principle of relativity. So the second question is, how does the particularities of GR reflect into the principle of relativity? So what we want is a good description of how can we describe this principle of relativity within the given theories that we will work on. So we have two different sides of the coin, if you want to think about it. The historical point of view. So we start from Newton. We developed his classical mechanics in the way he formulated it via absolute space, time, and motion. Then after this, we introduced the inertial frames that were proposed posterior to him. And then we go to electrodynamics, the problem of the ether, the simultaneity of time, and we arrive to special relativity. And from that, we try to describe gravity in terms of the foundations of special relativity, and via the equivalence principle, we arrive to general relativity. Okay, so this would be if we would read like a history book of physics. But then we will also sometimes diverge from that because we want to explain, as I say, a common language to all of it. So we will also introduce what's called Newtonian spacetime and Galilean spacetimes and Newton-Cartan spacetimes, which are just formulations of Newton's physics in terms of geometrical language. And I think it's so anachronic that actually you don't even learn that in the course of physics. You learn that posterior because even though it doesn't tell us more that already Newton's theory told us in terms of physical consequences, it does tell us a lot about what makes GR so special. Then I will introduce Minkowski spacetime, obviously, and discuss about covariance and invariance of laws. There are different concepts and how they reflect on the theories, and also to discuss what do we mean by absolute and relative. I will give a precise definition to what it means by absolute and relative. And then we want to apply all this to general relativity and discuss the principle of relativity, if it applies, if it not, and if not, what do we have left about general relativity? Does it have some principle underlying it or not? Okay, is there any question at this point? Okay, I see. Okay, so let us start first with classical mechanics. And we will introduce first the classical mechanics, as I said, as Newton introduced it, talking about absolute space, absolute time, and absolute motion. At the end of the day, the recipe is always the same, right? We have some laws about motion, some laws about trajectory of particles, etc., some laws about forces or interactions. But in order to describe these laws, we need some space, time, and motion defined previously to it, okay? And both of these structures, they come together and then describe the theory that we want to describe. So if we start by Newton, Newton has the three laws of motion that we know. Oh, there is a okay. There are the three laws of Newton's mechanics, the laws of motion. First of all, every continues in its states of rest or uniform motion in a right line. The change of motion is proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. And to every action, there is always an opposed and equal action. So this is the typical laws you learn in the school and in the degree of physics, just written without formulas, but obviously you know how to associate to each of these statements some given formula with the force, the mass, the acceleration, etc., right? So, but what I want to focus here is on these colored notions. So even in the first law, we have a notion of state of rest, we have a notion of uniform motion, and we have the notion of right line, right? And these terms are not defined within the laws. So we need to give a prescription on what we mean by state of rest, uniform motion, and right line. So we require a ground, a given concept, definitions, a system of definitions for the dynamical laws. We want to talk about straight lines, circular lines, more generally, or distance. These are notions that come about geometry, and of course, in the times of Newton, the only geometry available was the Euclidean geometry. Okay, so basically, we have a Euclidean space structure that will give us a notion of straight line, circular line, a distance, etc. So we call this the geometrical requirement, okay, for describing the dynamical laws. But apart from this, we also need to talk about motion, uniform motion, and also accelerated motion or rotational motion, etc. And this we call the kinematical requirement. So for Newton, this was encoded in what he called absolute space, absolute time, and absolute motion. He already introduced it in the Principia. So what Newton says about these terms that he will define, he said the following: I do not define time, space, place, and motion as being well known to all. Only I must observe that the common people conceive those quantities under no other notion but from the relation they bear to sensible objects. And then arise certain prejudices for the removing of which it would be convenient to distinguish them into absolute and relative through an apparent mathematical uncommon. So we see already here the discussion about absolute relativity had started even at the beginning of physics, right? So what Newton wants to try to say here is that at his time, the discussion about motion really involved relative motion more than, what we mean by relative motion is not exactly the notion that we have about inertial frames, but really a notion about we describe any kind of motion of an object with respect to whatever other objects. And this discussion was not good enough to construct a mechanical theory. At least that's what Newton thought up in that time. And we don't have time to discuss it now, but it's very interesting why Newton said that. Actually, the Principia is full of texts of Newton try to argue things that we think are arbitrary, but they really mean something. And in this particular text, he's really referring. Oh, sorry. Did somebody talk? Oh. Can you hear me right? Or
we can hear you, yeah.
Okay, great. So as I said, Newton here was trying to make a clear distinction between relative motion, whatever that means, and absolute motion. And we don't have time to go into the historical details on why he did that, but if you want after this lecture today, you can ask me about it and I can maybe comment here more. So how does he define the different notions? So this is completely copied and paste from the Principia. I'm not saying anything on my own. So absolute space in its own nature without relation to anything external remains always similar and immovable. And then he defines what the relative space is about this. So here the basic notion is that we have a structure where you can, if you want to think about in terms of geometry, you can think about the Euclidean space. And what he means by this is that this absolute space is not influenced by anything external. So it's independent of whatever motion, whatever body, whatever force is acting. Okay, that's what we have to really keep in mind. From that notion of space, he defines the notion of place, which is just the part of space that the body takes up. This is a clear notion. If it is a part of absolute space, we call it absolute place. And if it's relative space, we call it relative space, we call it relative place. Just picturing it, we can imagine that if we are moving in a boat in a uniformly motion, we are inside the boat. You would say to yourself, I am in rest, okay? But we know if we go outside the boat is moving, so you are not really in rest with respect to absolute space. That's what Newton would say. You're actually moving, and if you are on the earth, on top of the earth, we know that the earth is moving. So all this motion accumulate, and they always refer to absolute space as moving, whereas you can find yourself maybe thinking of that you are in rest, but it's all with respect to relative space in that case. So these are the two different notions. In the case of time, absolute true and mathematical time of itself and from its own nature flows equably without relation to anything external, and by other names called duration. So here we mean exactly the same thing. We need a notion of time. Time flows equally, so meaning that there is a notion that we can say equal times are flowing, and it is independent on whatever motion, whatever force, whatever body is present, we can still define this absolute time. And finally, absolute motion, yeah, as I said, is the translation of a body from one absolute space into another. And relative motion, the translation from a relative place to another. That's the example of the boat. Okay, yeah, so maybe here I can maybe read this so that we really get an idea of what Newton is talking about. So absolute motion is the translation of a body from one absolute place into another, and relative motion, the translation from one relative place to another. Thus, in a ship under sail, the relative place of a body is that part of the ship which the body possesses, or that part of the cavity which body fills, and which therefore moves together with the ship. And relative rest is the continuance of the body in the same part of the ship, or if it's cavity. But real absolute rest is the continuance of the body in the same part of the immovable space, in which the ship itself, its cavity, and all that the conveys is moved. Wherefore, if the earth is really at rest, the body which relative rest in the ship will really and absolutely move with the same velocity which the ship has on the earth. But if the earth also moves, the true and absolute motion of the body will arise, partially from the true motion of the earth and in immovable space, partially from the relative motion of the ship on the earth. And so on. And so basically, we can always have relative motion, and we need to keep track on the cumulative relative motions that we are summing to give really a notion of absolute motion. So as I said, these are definitions, and it's important to really understand that they are definitions, because otherwise we could start to think about it, and this is an important it has been a very important discussion in philosophy of physics about what then space and time is really about. Because when Newton says it's absolute space, one can have a notion that it's okay, maybe it's something different from matter, and then one can give a notion of substance to it, and then one can really go to philosophical debates of what it means this substance to be. And as I said, has been a very important historical discussion. It started with Leibniz when he discussed it with Newton about it via Clarke. These are very famous Clarke-Leibniz debate on the substantivity or relativity of space. And it had even gone until today, where people still discuss on the metaphysical descriptions of the space, absolute space by Newton. But it's important that here we will just assume there are definitions, which what we mean is just, you can think of it as just elements of our theory that are not in principle measurements or observations, okay? In the same way, for example, we think about fields in quantum fields. These are structures that we need for theory, and they need to be defined precisely, and that's what we want to discuss. Are these definitions really precise within a given theory without invoking to any observable, right? We cannot observe a field in this case, and in a similar way, we cannot observe absolute space or absolute time in any meaningful way. But what we can ask is, are the definitions that Newton give to this concept meaningful? Okay. So as as I say, absolute space is the Euclidean space. It's absolute. As I said, it's independent of anything external. Absolute motion. What we want to ask about absolute motion is, can we differentiate between absolute rest and absolute motion, given our dynamical laws, given the laws of Newton? And for absolute time, we want to try to think if it's consistent to think about it as equably flow of this absolute time. If you want to think about it again in this more geometrical picture, we have here on the right hand side the idea of absolute space. So basically, we have a notion of absolute time, which what it means is that we have a universal clock, let's say, the Newton clock, if you want to think about it, which really tells us at each moment where are the points that lie within the same simultaneity slice, okay? So we want to know if two events have the same time, and we put them together in a slice, which we call S1, then we would have different slices, okay? Continuously flowing in the real line, if you want to think of it geometrically. And what absolute space means is that we have some straight lines here that I call F2, and that will allow us to say if something is at rest or if it's moving with respect to this absolute space. So for example, F1 would be moving uniformly with respect to absolute space, which I define as F2. But if I would have lines parallel to F2, then of course this would mean that this body, the evolution of this body is at rest with respect to absolute space. Okay, so if you want to have the geometrical picture. Okay, so question then: are these definitions consistent? So for the time, the answer is yes, it is consistent, because we can always use the laws of motion, the laws of Newton, to at least construct universal clocks with arbitrary precision. Okay, that's what we expect from this definition to be consistent. So the idea is that there is nothing arbitrary in our definition of time as flowing absolutely. Actually, historically, the notion of an universal clock would be the stable stars on the sky, right? We know that they flow uniformly, at least to a very great precision, and we can use them as these universal clocks that flow uniformly. Now, one can say, well, the stars are not exactly uniformly, and then you are right to say that. But the thing here is that we can always use the dynamical laws to know which forces act on these stars, and then actually always precisely correct this clock by applying the laws. So even though this absolute time is not perfectly measurable, the notion is consistent in the sense that we can always precisely use the dynamical laws to approach the limit of absolute time. And a trivial consequence is that even though people really criticize Newton for using the absolute notion of these concepts, actually absolute time has been present in most of the theories, even up to the last century until special relativity. Okay, so, and then what about absolute space and absolute motion? Well, here that doesn't work anymore. So we find that these notions are not consistent. Why are they not consistent? Well, because we know that the laws of motion, they follow what we call the principle of relativity. Historically, Galileo was the first one to try to formulate it, but when he applied it, he first referred to circular motion as being a part of the principle of relativity, but then Huygens formalized it, applying it only to rectilinear motion, and then Newton actually used it in the Principia. And here it's formulated as Newton formulated it in Corollary 5 of the Principia. The motion of bodies included in a given space are the same among themselves, whether that space is at rest or moves uniformly forward in a right line without any circular motion. Okay, so here what it's saying is that you have a given space, and if the space is moving uniformly, whatever is inside the space, whatever bodies they are, whatever force they act upon, you cannot do any experiment to know at which velocity the space you are inside is really moving. Okay, this is the typical example of the boat that you do any experiment and you realize there is no way of knowing how what velocity are you moving within the boat. In more modern terms, if you want to think about it, basically what it means is that the laws of Newton are invariant or the Galilean transformations. Okay, and this also means that you have some notion of inertial frames, and they are indistinguishable from in terms of experiments. Okay, so for us, then what this means is that the notion of absolute rest and the notion of absolute motion are completely arbitrary. So we cannot use the laws of Newton, the laws of mechanics, to discriminate between absolute rest and absolute motion, because we know that any system that moves uniformly will obey the laws of dynamics in the same way. So this indistinguishability, it doesn't allow us to define precisely what is absolute rest and what is absolute motion. So these concepts they are not, they are completely arbitrary. And then as definitions, they are problematic, okay? Now, one can ask the following question, okay, if that's true, how really did Newton work? How did he produce physical consequences that we know? So as a review then, okay, Newton requires absolute time, space, and motion. That's how he defined his dynamical laws in the Principia. But as we saw, only absolute time is definable within the laws of mechanics. We can't have a notion of absolute rest or absolute velocity due to the relativity principle. Just an exclamation, we do have a notion of absolute acceleration and not absolute rotation. Actually, that's one of the reasons that led Newton to impose absolute space. I mean, Newton, of course, knew that you could not discriminate between absolute rest and some constant velocity. He already proposed it in the corollary. So it's not that he was trying to contradict himself, but he was really thinking of absolute acceleration and absolute rotation, that we really know that the laws really allow us to discriminate to infer absolute space. And there has been a lot of philosophical debate around that. We will not go to this debates, but they involve the bucket experiment. Maybe you know there has been a lot of discussion about the meaning of absolute acceleration, absolute rotation with respect to absolute space. But as we say, even for the notion of absolute velocity, this is we cannot do a unique, precise way to absolute space, so we try to put it aside. Now, for Newton, there were two relevant theoretical contexts that he wanted to discuss in the Principia, physical systems. One was the traditional problem in astronomy of distinguishing true from apparent motions, as we saw, and determining the true structure of the planetary systems, where he was mostly involved with. And the second was a contemporary problem in physics, that state of distinguishing states of motion by the physical causes and effects. Now, let us focus on the first one, on the structure of planetary system, to see how he was thinking about the dynamical laws and absolute space and so on. So the big debate, or the big question that was proposed at the time of Newton was, okay, we know that Galileo said that the sun is really the center of the system, of planetary systems, contrary to the Earth. But for the philosophers at that time, or the physicists, philosophers, if you want to think about it, this was not clear at all, because we had, as I said at the beginning, the discussion was really thinking of motion as a relativistically, you want to think about it. So it was relative motion that was really the physical motion people thought about. So the question of whether the sun is in the center or is it the Earth, it didn't really make sense. Okay, you could describe both of these ideas. It's just that if you put the sun in the center, then the motions are simpler than if you put the Earth on the center. Now, for Newton, this was not acceptable. Actually, he really wanted to give an answer to this. And the answer to this we find in Corollary 4. The common center of gravity of two or more bodies does not alter its states of motion or rest by the action of the bodies amongst themselves, and therefore the common center of gravity of all bodies acting upon each other is either at rest or moves uniformly in a right line. So here we have two things. So the answer to what is the center of the planetary systems for Newton was the center of gravity, which is something that you can actually compute given the forces and the motions of the bodies. And this point, which was not the sun, but also was not the Earth, was exactly the center point for him for the planetary systems. Now, what he argues is that the sun, because it's very massive, is very nearby to this point. So actually, to a very good approximation, the sun is really the one that is at center. This is the first thing that he realized. But the second thing is that then he says, well, yeah, this center of gravity, which acts as if no force is acting upon it, so it moves uniformly, can either be at rest or uniformly, and we don't know. So it could be possible that all the planetary system is really moving uniformly or is at rest with respect to absolute time. Okay, as I said, all these kind of definitions are with absolute time, sorry, with absolute space, but we are not able to know if it's one or two, but we still can answer a physical question, okay? We can really say that the center of the planetary systems for him was the center of gravity, okay? An interesting fact that will come now after this is that this point is not really a material point. So this is a point in space. And actually, we will see that basically this point, you can think of it as just an inertial frame, okay? Because this point is not affected, the center point of this gravitational system is not affected by any force, by definition, by construction. So one can use it as an inertial frame. So actually Newton really thought about the idea of an inertial frame already in the Principia. He just didn't have the tools, mathematical tools that came after to really construct the whole notion of inertial systems in an inertial frames. Furthermore, still working on the planetary systems, he also proposed Corollary 6, which is even more, let's say, it's even stronger than the before, because he says, if bodies move it in a manner among themselves, are urged in the direction of parallel lines by equal accelerative force, they will all continue to move among themselves after the same manner as if they had not been urged by those forces. So what he means by this is that if we have a system of bodies and we accelerate all of them equally in the same direction and with the same magnitude, then this system does not have any way of knowing if it's accelerated or not. Well, we know that this is a very, 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 very similar way of actually the equivalence principle, okay, which then Einstein connected with gravity. And actually, Newton applied this corollary to understand the satellites of Jupiter, because the satellites of Jupiter and Jupiter itself, of course, have different forces acting upon them because they have different distances from the sun, for example. But since they are so far away, we can actually assume, to a very good approximation, that the satellites have the same force parallel to each other with respect to the sun. So we can actually think about the Saturn and his satellites to be really an almost inertial system. And we can apply the laws of Newton that know about these inertial systems to this kind of system, even though we know that the whole system has forces acting on them. So one can think of it as that Newton was really aware of this whole idea of relativity with respect to uniform motion. He even extended it to accelerated motion, although one have to be clear that this is not really a relativity principle, this corollary 6, because it's only approximative, okay? And furthermore, one knows that if we have we accelerate every body by the third, we will have a force acting upon whatever produced the acceleration. So we will have a discrimination of knowing what's happening, okay? So the principle of relativity really is just focusing on uniform motion, and the accelerated motion here is just something extra that we can propose, but we don't include it as the relativity principle in the same way as we do the one about uniform motion. But I just want to stress out that in Newton applied the notion of relativity to construct what you call pseudo-inertial systems to really do the physics. So even though he defined his laws in terms of absolute space, absolute time, and absolute motion, he knew that there was this arbitrary way of defining systems, and then you can use it to your advantage, actually, to to have physical answers, in this case about the planetary motions, okay? And there is a nice article by Desai of 2020 that he calls Newton's relativity theory, which seems a bit ironic, but it's this whole idea that Newton really applied the techniques of the principle of relativity to understand planetary motions. Okay. Okay, so do we have questions up to now? I don't know if there should be a pause, or should I just continue, or?
Well, it's up to you. If people want to ask questions, they are free to raise their hands or
Okay.
unmute themselves or type in the chat and I'll read them. Okay, we have a question, I suppose. Okay, maybe not. So,
Okay.
so cool.
Okay, so I will continue then. Okay, we can maybe finish earlier. So we have this idea of Newton of absolute space, time, and motion. We know that Newton used an extra, the idea of the principle of relativity, to apply it to physical systems. But then, of course, from the more fundamental point of view, one can ask, okay, then how can we still describe the laws of motion, the laws of Newton, in a way that we don't require absolute space? And this is a very good question, because obviously we don't want to build theories on concepts or on definitions that are not consistent within this theory, okay? So this is when the ideas of reference frames and inertial reference frames came about. I will just briefly introduce it because most of you are familiar with the idea of inertial systems. So to precisely define it, there are many ways of doing it. I will just explain the most basic one. So we first start with a given body that has some given motion, okay? Actually, if one wants to be a bit more precise, one would have to define 4 bodies moving in order to construct what a frame is, okay? You can think of it as you have the Cartesian frame, for example, you have 3 lines, and these are just 4 points connected that are non-coplanar in order to define a consistent system. But let us just assume that we can do that, and we call it a body. Then we add to it a coordinate system and a time scale, okay? First, a coordinate system here is in space, 3-dimensional space. It's just labels, how we say about position, and a time scale that tells us what time do we measure, okay? Here we are implicitly assuming that all possible bodies, they will have the same time scale, okay? Just you can choose maybe the origin, but we have a separate notion of a coordinate system to each frame and a notion of time scale, okay? We are not talking about space-time yet, but differences between space and time. So going back to our picture, now what we would think about this idea is that we don't have a rest, an absolute space that would be F2, but actually F2 on F1 are completely indistinguishable. So they have the same right, each of them, to say that I am a frame, okay? And that's the whole idea behind the relativity principle, okay? We will still have simultaneity slides, because I have said absolute time is consistent, so we can still use it to define the same time at each moment. But then how the frame moves in the space-time can be arbitrary. Now, we want frames, but we want frames that follow the laws of dynamics. So, and of course, when Newton proposed the absolute space, he was thinking that some motions do not agree with the laws of dynamics. Okay, you can think of an accelerating motion rotating will not see the dynamics of the laws of motion. So then here, what we want is to, okay, from all the possible bodies with all possible motions, we will select a precise family of these motions that see the laws of dynamic as Newton wrote them. And we call them an inertial systems, okay? So Bergman defines them in this very precise way. There exists a class of frames, so this is important. There exists means that we already assume they exist, okay? We are not they are not consequences of any physical law. We assume they exist just in the same way maybe as Newton think about when as absolute space, it exists there, and we just define it. There exists a class of frames called inertial frames, and inertial frames is a frame relative to which the laws of inertia hold, relative to which a particle free of impressed forces either remain at rest or else continues in a state of uniform rectilinear motion. Okay, so there's a lot of things to say about this because basically one can easily fall into a circular argument, because if we say that the laws of motion are defined with respect to inertial frames, but we are defining inertial frames as the ones that we see the first law, then of course the first law becomes completely circular. And here, the way of solving this is that we replace the idea of the first law not to be an empirical law, but actually be a definition of what we call inertial frames. And then we apply it to the second law. Okay, so there are some consequences when we introduce inertial frames that Newton didn't have to do because Newton had absolute space. But in our case, we require, if we introduce inertial frames, to be very careful on the structures of laws and what they mean, if they are laws or they are just pure definitions. So these are the usual way that people work with classical mechanics that we studied the first years of degree. We get some coordinate systems and we write the laws in these coordinate systems, and we just assume they are inertial frames. Okay, and then we can use, for example, we can understand the motion of a pendulum by assuming that the Earth is an inertial frame with some coordinates that we can define distances and so on. But of course, if one would be precise, we know that the Earth is not an inertial system. It's just that, okay, we assume really it is exactly the same as really Newton did. So we are not really changing things. It's not that we are creating a different theory of that Newton did. It's just that we are reformulating the ways that the theory is founded, so that at least it makes sense from the point of view of interpreting the theory as really existing objects. Okay, so now if we have dissolved the notion of absolute space, we can maybe also dissolve the discussion of if space is a substance or not, because it's not really part of the theory anymore. But these inertial frames are, and then one can really ask, what are really inertial frames? Because they are just exactly the same structure as absolute space, in the sense that we don't see inertial frames. Okay, you can maybe think of bodies being almost inertial frames, but we know that really there are no real inertial frames, because we know that gravity is universal, and since gravity is universal, it will affect all bodies. So there is no body that is in absence of forces, and therefore we can only think really of inertial frames as being these abstract objects that we define consistently, but they have not material structure in any way. Okay, so we can force more the idea of dissolving this kind of abstract notions, and then one can ask the question, can we describe the laws of mechanics without invoking inertial frames? So, and more generally, since inertial frames are associated with coordinates, can we describe the laws of motion, the laws of Newton, in a coordinate independent way? Okay. So I want to answer that question, but I think maybe now we can maybe do 10 minutes pause. so
Could
that
I
we can
ask a
also.
question before that?
Yes.
So, well, thank you for this distinction. Well, I think this puzzle of apparent recurrence between the first law and inertial frames has puzzled me for a very long time. And I wonder, um, is there an operational prescription of how you identify an inertial system? Of course, if you have this absolute space, as you mentioned, then you can define it mathematically. But here in my lab, how can I know if I'm in an inertial frame?
Yeah. Yeah. So yeah, that's a very good question. So um the idea here is that you can use the laws to actually operate and find, well, not you cannot construct an inertial frame because by definition it's the absence of forces. And the only way you could do that if you had only one body in the universe. So operationally, that's the only way you could. But what you can do is you can use the dynamical laws to know if you are on an inertial frame or in a non-inertial frame, because you know that only inertial frames see the laws of dynamics. So if you are able, doing all the experiments possible, you can always determine if you are moving, accelerating or not, because the laws of Newton allows you to discriminate between accelerated motion and non-accelerated motion. You would see, for example, Coriolis forces, or you would see what we call in the degree of physics, fictitious forces. And if you have precise experiments, you can always determine them. So operationally, you could do it to see if you are deviating from inertial systems. Now, the question is that operationally, you can never construct an inertial system. So that's problematic because you are requiring, in a sense, the absolute space to be operationally possible, which is not. And then the inertial frames, they do slightly better, but we can only assume that inertial frames by definition exist in the same way, almost in the same way as absolute space, in the sense that they cannot be really constructed by material objects, because by definition, material objects will have, to begin with, gravity as a universal force, and therefore, the moment you construct material objects, they will not never be inertial frames.
Yeah, I see. That's very interesting. At the same time, there is I mean, I like what you said about knowing the dynamics. I can identify if I am whether or not I'm inertial, but that's a lot to know, right? Because then I need to know all the true forces of nature,
Yeah. Well,
right?
actually, if you read the Principia, Newton starts with this claim. So Newton really thinks methodologically that you are able to know about all the forces in the universe. This is an assumption, of course. You could argue that maybe this is not the case, and then you could you had to rephrase the laws of dynamics. But the assumption is that, in principle, by knowing, so Newton starts by knowing the motions of some object, you could deduce the forces, and by deducing the forces, you could deduce the possible new motions of that forces. So the whole idea is that, in principle, you should be able to do it. But of course, one can argue that maybe nature is not like that. And maybe there are forces that do not allow us to do that. And yeah.
Well, thank you.
So if there's no other question, I would suggest maybe 10 minutes break.
Sounds
Come
good. So I'll
back.
pause the recording and we'll reconvene in 10 minutes then. Yeah.
Okay, perfect. Okay, so just to sum up until now, we have seen that Newtonian laws of motion, they force us to give some structure of space and time. Newton proposed an idea, a concept of absolute space, of absolute time, and absolute motion. We saw that the absolute time notion is consistent with his theory, and the idea of absolute space, not so much, because we cannot differentiate between absolute rest and absolute motion because of the relativity principle that makes indistinguishable two bodies that are moving uniformly to each other. Both of them have the same right to say, I am absolute rest. So the whole idea of absolute rest is completely arbitrary. we can relativize in that sense absolute rest. We will see that this is the main philosophy of all this course. Basically, we have some notions that we think they are absolute. We think they can be defined absolutely. And actually, the laws that the proper nature is given to us are forcing us to relativize these notions, right? And Einstein's dream was to relativize all the possible notions of space and time, meaning that we do not have to give any prescription on absolute motion or privileged motion or anything to talk about the laws of physics. So this will be the line, and we will see if this is successful or not. Now, we saw that we can also introduce inertial frames, which makes the life simpler, both because we can easily compute things, but actually also because we don't rely so much on absolute space. But then, of course, the question is, what are these inertial frames? We, as Per one says, we assume they exist, but we know that they are operationally impossible to achieve. So we are in a similar state in the sense that we still have some abstract notion that is there. And then the question is, can we get rid of it? Can we get rid of inertial frames to define the laws of motion? This is parallel to Einstein's equivalence principle, because as we will see on Thursday, the whole point of Einstein is to dissolve the ideas of inertial frames because they are indistinguishable with respect to a gravitational force, at least locally, but enough to say inertial frames are really nothing special is about inertial frames, and we should avoid constructing our theories depending on these frames that should not be anything privileged, okay? So in order to do that, I mean, this part is completely non-chronological because obviously Newton did not have any tools of differential geometry. But I will try to describe Newton's mechanic in terms of modern structures of differential geometry. In order to do so, I will first, of course, introduce some of these tools before talking about Newton in the context where they are mostly known in physics, at least, which is general relativity, okay? Most of you maybe didn't have a proper course on the geometrical description of general relativity, but yesterday there was a course, right, that introduced these topics. So I will go a bit quickly. But the whole point at the end of the day is to describe our theory, in this case, general relativity, as laws that are completely independent of coordinates, okay? This is the basic idea, and of course, this makes our life a lot complicated in terms of mathematics that we need, but at the same time, it really allows us to focalize on the structures that we require for a dynamical laws to exist. And that's exactly what we need in order to know exactly, do we need absolute space? Do we need inertial frames? What do we exactly need to define Newton's theory? Okay. So this will be a common language of our theories of Newtonian physics, of special relativity and general relativity. So it's worth to spending some time, even though I will go a bit quickly, but some time on the different notions, okay? So the language here is basically structured in different levels, okay, from the most basic one up to the most strong one. And so the ground floor where we start with space-time theories, it's what we call M, which is our four-dimensional differential manifold, okay? Well, before that, let me just point out briefly what do we mean by space-time theory. So basically, we have two ingredients, okay? We have, for at least classically, okay? We have a space-time and geometrical structure, okay? If you think in terms of GR, it will be obviously the manifold and the metric, if you want to spoil the what I'm going to say. Plus, Second part is some matter fields, okay? Could be some distribution of mass, it could be distribution of charge, it could be the stress anything, it could be whatever field structure you wish to define describing matter, okay? So these are the two ingredients that, at least for classical theories, we would require. We will focus only on the space-time and the geometrical structure. So the first element, as I said, is the manifold, okay, the four-dimensional differential manifold in our case, because we're talking about space-time. Here we are already talking about space-time. Before we were talking space and time separately. Here we discuss about space-time. We can define in the space-time as just a set. Okay, you can think of it as sets of all possible events that can happen or that don't happen, whatever, all the possible points that have some space and some time, if you want to intuitively separate it, but we are really talking about a four-dimensional set that has some extra structure, okay? Because obviously a set is just points, and we need to talk about continuity. So we want to talk about a neighborhood of the space of this in each point of the set. So we require a topology plus what makes it really a differential manifold is that at each point we have some given maps such that these maps translate us the point and some neighborhood of our manifold to the reals, the four-dimensional real space-time. And these maps, well, they need to be sufficiently continuous, etc. But this allows us to use our techniques of the reals applied to our manifolds, okay? And these maps, we call them coordinate systems or charts, okay? Already coordinate systems is telling us something similar that we discussed before, but here we are really talking about mathematical maps until now that just for each point in P of the manifold gives us, if you want to think of it, four real numbers, okay? Something to say about this is that all our definitions will be local, meaning that they will only refer to a point in a neighborhood. We are not talking about global features of space-time. Maybe you will have some lectures about that, but we don't require it for understanding. So really everything is just defined only in a point in a neighborhood. We don't require anything to be global defined. Okay, so apart from the manifold, this is the first structure. We need, of course, talk about trajectories, to talk about motion. In this case, we define a curve. What is a curve? Well, it's just a map. You will see that basically differential geometry is just basically the definition of a lot of maps. In this case, the curve gamma is a map from the real line. You can think of it as a parameter time that will give us the curve from the real numbers to the manifold, okay? As the picture here shows, we have some real line, and then from each point in this real line, we give a point in the manifold, okay? And this will define the curve. Now, a curve is not enough. We want to talk about straight curves. We want to talk about how a curve bends. We want to talk about curvature, etc. So these notions require something extra, right? And the way we define it, again, because we are forcing ourselves to define it locally and in coordinate independent way, we define what's called the tangent vector space, okay? So the tangent vector, we define a tangent vector given a curve at a given point of the curve as written as I put there, okay? So basically what this vector is it acts on a given function where this function is a smooth function, okay? We act on this the tangent vector, and we give this value to each function for a given curve, okay? So geometrically, okay, you can think of it as the tangent vector of the curve at each point P in the curve. How can we see that? Well, if you use some coordinates very quickly, even though this is completely defined without the reference of coordinates, but if you introduce coordinates, you can see that this notion of tangent vectors appears. as we would think of it in terms of Euclidean, for example, Euclidean 3 space, where that's exactly, we define the tangent vector as that kind of velocity vector in some way, in this sense, okay? Now, what we can do is we put in a set all the possible tangent vectors for every possible curve that goes through a point, and for each point, we can define then the tangent space at this point, okay? We can show that this is actually a vector space, and this is enough for defining the structure that will come now. Now, well, that's not completely true, because we usually want to talk about not only a given point, but actually some motion, okay, that connects different points. But since the point structure, so the manifold structure is not a vector space in this case, it's a bit more tricky to connect one point to another. But one ingredient that we require to do that is what we call a vector field. So the vector field, what we can do is at each point, for each point, we can give one vector that lies within the tangent space of that point, okay? Now, an extra idea, an extra concept we require is to talk about what does it mean to move in the same direction, okay? If you want to think about parallel transport, okay? And for that, we need what's called an affine connection, which is just an or derivative operator. With how does it work? Well, this for a given curve, we have some given at each point we have some tangent vector field. No, sorry. For a given curve, we have a tangent vector field, which basically defines one tangent vector for each point of the curve. And what this operator does, it basically transports the tangent vector from some given point to another. Okay, so here we can see how does this apply. We start in the picture. We start for a given tangent vector in P, and then what this derivative operator does is that it shows us how this is parallel transport up to the point Q, and then we can compare the tangent vector at Q with this displacement of the tangent vector of P, and comparing both of these vectors, we can then give some idea of how the curve has bent, or how the curve is parallel transport or is not, and so on, okay? And that's exactly what we can do in order to define a geodesics, okay? So usually when you have the course of GR, the metric is already introduced, but this is not required at this level. We can already say about what is a geodesic in the same of a curve that has the straightest path. So the tangent vectors are as parallel as possible. And what this requires is that this derivative operator applied to the same tangent vector has to be equal 0, okay? And then we can talk about how this curve behaves, but for us, the main point which I will use in the tomorrow and on Thursday will be that the geodesics already allows us to differentiate of what we can call curved spacetime or curved geometry or flat geometry, okay? There are two ways of seeing that. Obviously, the most known one is from the affine connection or derivative operator, we can compute the curvature. If the curvature is 0, then it's a flat geometry. If the curvature is not 0, sorry, somebody's silent. If it's not 0, then it's curved, okay? But we will use this other similar definition, okay, or implication, as you can think of it as you want. And that's the idea that in general we can use the geodesic equation and write it in terms of coordinates. In this form that maybe you know from GR. And then what we have there is what's called the Christoffel symbols, or the affine connections, which are just numbers, these gammas. And it's given by whatever you give me about the affine connection, these gammas. If I give you the gammas, I can give you the affine connection. So you can write it in general coordinates as this. And then what we define is that we say that the derivative operator is flat at P if there exists a coordinate chart, we call it Y, such that these gammas are zero, okay? All the components of these gammas are zero. So if we can find such a coordinate for any point of the manifold, that's important. Then this is we call it a flat, a flat geometry. And we call this coordinates Cartesian or inertial charts. Of course, this name will be connected with inertial frames, and we will see that tomorrow probably. But here we are talking about really mathematical definitions, okay? The physical notion comes about because if these gammas are zero, then of course we are left with the second derivative of this coordinate chart, and this basically defines the acceleration, and what we say is that there's acceleration zero, so it's like a notion of inertial frame in this configuration. Of course, one has to be very careful here because we have not defined space and we have not defined time as separate things. We can do that, we will do that but at this point it's not the inertial motion of space and time in this sense. Okay. So finally, the extra term concept of structure we usually add in GR is the metrical structure, and the metrical structure is all about measuring distance. Now, usually you measure distance in Euclidean space-time by taking 2 points and connecting them through a line, but of course in a manifold structure, this is general manifold structure, this is not possible, and the nearest way we can do that is by invoking some metric. So in the Riemannian case, we can define a Riemannian metric as a bilinear real value function on the tangent space at each point satisfying the following conditions. There you have it. So basically we take two vectors, tangent vectors if you wish here in our case, and for each point we give a number, okay? So this is what this metric does, and if it satisfies the three connections, we call it three conditions. It's called the Riemannian metric. If it only satisfies the last two, so it's not positive defined, we call it pseudo-Riemannian. So GR uses a pseudo-Riemannian metric because actually the metric can be either positive, negative, or even zero. With this metric, we can obtain a notion of length of vectors, angles between vectors, and length of a curve in a meaningful way. And from this, we obtain what is called a metric geodesic as the curve that extremizes this length, okay? In the same way as the geodesic of the affine connection was the curve that has the most straightest tangent vector at each point. Here we have the smallest distance curve, okay? But you may realize that these are two different properties, okay? You can define the affine connection on one hand and the metric on the other hand, and actually this is not the case for GR. The GR is connected, we will see both of these things, but there can be other alternative theories that do have different affine connections and metric structures, and these notions are independent. Okay, so analog to the affine connection, now we can talk about flat or curved geometry here in this sense in a very equivalent way. So given some coordinates, we can write the metric as follows there. And then if we ask the question, can we find a coordinate chart such that we can diagonalize the metric to 1, 1, 1, 1 in different signs? And if the answer is yes, that we can find it, then we say that the space-time at this point is flat. Okay. Now, as I said, if we have a metric, there is actually a straightforward way to construct an affine connection by just implying this condition there, okay, that the derivative operator applied to the metric is 0. So this condition provides a uniquely defined affine connection, okay? Given the metric, you have the affine connection. So this idea of flat and curve, it's connected to each other in this sense in GR, okay? Actually, in GR, the question whether you can find these coordinates, it's answered as yes, but only locally. So meaning that on each point, you can define an coordinate system. So at each point, you can define it as being flat, but the moment you go away from that point to even a neighborhood, it is non-zero. So it's you can call it locally flat. Okay, that's the notion, even though it's not strictly well defined, because the moment you have a neighborhood in the neighborhood, this is not applicable anymore. But for example, in special relativity, you can do it, and it's completely, and that's what we call special relativity as having a flat spacetime. Okay. And okay, so basically the definition then of general relativity being very fast is the spacetime is a differential manifold with a Lorentzian metric, a pseudo-Riemannian metric with signature 1, 3. This is just, I will not go to explain what a signature means, but not important, but there's a clear definition of what a signature is that satisfies the Einstein's equations, okay? The ones that introduced before, and by, very good. Also, to be very mathematical rigorous, you usually need a time orientation, and you usually want your spacetime to be globally parabolic, but these are just mathematical extras you can add to your spacetime. With this idea, we can define already GR. From that, you can define the curvature, the Riemann tensor, so on and so forth, which you already know how to do. We don't require it here, at least at this level. But what I want to highlight is that we have different levels of structure that we can add to our spacetime. And the way we do that, it depends on the laws we want to define. Okay, for GR, Einstein, after almost 10 years, and I will go to that on Thursday, required the notion of a metric. But the idea of a metric is just something that was really thought about a lot. It's not something that it's implicit in space-time, okay? And in order to see that, we are going to finish today's lecture by studying Newtonian space-time, okay? And here I'm referring to space-time connected to each other, not talking about space and time. Okay, so, well, this is just a stop, so I let the intermezzo, it's finished, and we go back to Newton. Again, with the first law of mechanics, everybody continues in a state of rest or of uniform motion in a right line. Okay, so what it means is that if we want to think about this law in, let's say, space-time, now not space and time as I draw before, but really in space-time as the picture there, we see actually that it is a straight line. So why are we saying it's uniform? Well, we are saying it's uniform because we are separating space and time. We are saying uniform motion, the definition is we have same distance and same time. But if I connect space and time, then actually I don't need to talk about uniform motion. I could talk about straight motion in space-time. This is the key idea of thinking about space-time. And then we can differentiate between accelerated motion, for example, in the second picture, where we have a first section of uniform motion and then uniform motion at different velocity, if you want to think about it. But a straight line in space-time is already what a straight uniform line is in space and time. Okay, so here's the key role to think about how we will interpret Newton's spacetime. So we encode the notion of uniformity as a straight line in spacetime as follows. In the classical formulation, we have some trajectory that you give me the time, which lies in the reals, and I give you a vector, okay, which is the position of that trajectory, okay? Now, what we can do is we can amplify this and define what we call the world line of the particle as just doing the same thing, but in 4 dimensions. So you give me here in this case the time. Okay, we will generalize this to not to the time, but to other coordinates. But given a time, I can define you 4 numbers now, not 3. That includes the time on its own. Okay, and you think that this is absurd to do it, but you will see that this actually lead us to a good formulation. Now, if I do that, okay, then what I can do is I can restrict, since I have chosen the word line to the first element of the t to be t, then I have this restriction that the first time derivative of the 0 component of my new word line is 1. And then what I can do is I can define the first law and the second law of mechanics. That is the the left hand side written in this coordinate system, or in general, how you would think of it in terms of inertial systems or inertial frames, as the right hand side. They are completely equivalent. I just wrote in a compact manner in a four-dimensional space-time. So if you see the right hand side is basically written in these coordinate systems, just a geodesic equation, okay? Where here the gammas, which is the connection, the affine connection, is just this force that is implicit in the left hand side. Now, an important detail, of course, is that this is valid only for one force, which is the gravity force, okay? So the only force that is like the left-hand side written in this manner is the gravity force, because otherwise for other forces, the F would not be universal, okay? And then it would depend on the mass of the particle and the charge of the particle. We're talking about electromagnetic force and so on and so forth. So the whole idea here is to take into account that inertial mass and gravitational mass are the same thing, which is the core of the equivalence principle. I'm not going too much detail of this because I want to explain that again on Thursday when we talk about general relativity. But even in Newton theory, this is true. And so we can write the left-hand side in terms of the right-hand side, where these affine connections are just F that don't have anything to do with the composition of the body. So every kind of body, whatever its composition, will have this form of its motion, okay, for only if you want to think about only gravitational systems. So what can we do now? Well, we can, given this affine connection, we can compute the curvature. Sorry, I didn't explain how to compute the curvature, but hopefully you all know how to do that, and probably also the course of yesterday, they explain how you construct that given the affine connection. But if you do that, you get this form with respect to this force F, that would be here in this case the gravitational force. And then the 0, 0 component. So sorry, these are only these are the components only that are non-vanishing. And now what do we do with this? What does it mean that the 0, 0 component is this term? Well, if one is a bit smart, one can realize that if I define this F by just being apply the partial derivative of the gravitational potential in the formulation of Poisson's law of gravity, then the 0, 0 component, one can apply Poisson's law, and one can realize that this is just 4p Newton's constant times the energy, the mass energy density, in this case, the mass density of the body. So basically, what we have found in this very quickly, the very not so nice way of thinking about things, but we have just found that there's an equivalent way of describing Newton's laws that just assume that we have some given space-time and that it's curved, it's not flat, because the connections are not 0, that depend on the mass content of the system. So in other terms, Newton gravity, we can think of it in this formulation as being curved space-time. We have geometrized away gravity, okay? and only gravity, okay? Not generic other non-universal interaction. So we can only do that with gravity because of the whole idea of the equivalence principle. Okay, so this formulation that it's coordinate dependent, which is a bit not so rigorous, one can actually do it more rigorous. And I will briefly explain how. I will not go into the details because otherwise we would need a whole lecture to do that. I refer to you to Malament's book on this. The fourth chapter is a beautiful way of formulating things of Newtonian space-time, precisely with exactly like the same as we would do in GR with how I did before, with all the theorems and also. So I refer to you to this book of Malament. I will briefly explain how it's formalized. So one starts with what is called a Galilean space-time. So we take away for now gravity. It's just, let's say we are back into Newton's world where we want to define the first law of motion. So a Galilean spacetime is a quadrupole that has four elements. We have the manifold M. As I said, the manifold will be universal for all theories. And a fine connection, of course, we want to talk about motion, plus two other things, okay? We think now we don't have a metric anymore as we would have in GR. We have no metric. We have two other elements. dt, which you can think of it as a one form, you can think of it as a covector that has to do something with time, and h, which is so you can call it a pseudometric, but it's not exactly a metric by definition. But it will give us a notion of a metric. It's a two tensor. Here you have it in terms of like modern terms, in like Waltz notation, if you want to think about it. And this is exactly the structure that is independent of coordinates in the same way as GR that we require for the Newton's laws, okay? So as I said, as M is four-dimensional, here we're talking about space-time, as in differential manifold, as in GR. Then we have the affine connection, which in our case will be flat in Galilean space-times. We are not talking about an interaction, it's a free particle. The geodesic equation is as before, as in GR. So since we are in a flat connection, there exist some coordinates that we can write the geodesic as here, as this, which seems almost the first law of mechanics, right? We just have, in terms of not time, but u, and actually one can show, maybe I can show it tomorrow, I don't know. One can use the fact that there is a notion of time here, of absolute time, that will be formulated by dt to write this in terms of second derivative of the coordinates in terms of time, and then one had the first law of mechanics. So really with this formulation that is coordinate independent, given some coordinates, we can arrive to the usual formulation of Newton's mechanics. Now, but in order to do that, we usually, when we are talking about derivative of time, we have to have a notion of time and a notion of space. And this is exactly what these other two structures do, okay? The dt, with some formality that I will not go to, allows us to define a universal temporal function, a global temporal function. We could call it absolute time or the absolute clock, if you want to think about it. And we can use that to define simultaneity slides, because more formally, if you know what this means, one can define a notion of space-like vectors, one can define a notion of time-like vectors rigorously with the structure, and then one can realize that the space-like vectors, they are subspaces, and then one can foliate the space-time in a uniquely way, okay? This is the precise thing that will differentiate us from special relativity, where we cannot do this in a unique way. Actually, we will realize that these slices are not unique, but here, since we have this geometrical structure dt, we can do this in a unique way. Well, a unique way up to origin transformation. So we can always do t plus a constant, and then this is also the same dt, of course, because we're differentiating. But apart from that, it's always the clock flows the same, as Newton said with the idea of absolute time. And what we do with h, very quickly, it's not so important. Well, it's important, but not for here. For each simultaneity slide, it's the notion of distance, okay? We can define for each two events that are simultaneous, we could, in principle, construct a notion of how to connect them and a distance. Okay, so this is the Galilean spacetime. Very quickly, as I said, if you want really to get into it, I would recommend you the book by Malament. Now, if we want to include gravity, we can do that. Okay, it's also in Malament's book, but this was done by Cartan and then by Friedrich and other people some decades ago, to include gravity into the coordinate independent way in a rigorous manner. And very quickly, just to finish this, I have this proposition, this lemma that we can prove that says, let the spacetime M with T and H and the affine connection be a classical spacetime where the affine connection is flat, so a Galilean spacetime. We started with a Galilean spacetime as defined before. Further, let phi and rho be smooth real valued functions on M satisfying Poisson's equation. Basically, here we are thinking of phi being the gravitational potential and rho being the mass distribution. And finally, we can redefine another connection. I hope that you saw that yesterday. So we can two derivative operators, so they can differ from each other by this form there, this C, and both of them can be completely rigorous, defined, and then can differ from the C. So if we now redefine our affine connection in this way, then we have the following results. So our new spacetime, that is exactly the same as the Galilean spacetime, but we have just put here a new affine connection that includes the Newton potential, is also a classical spacetime, okay? It allows us to define the same simultaneous slice. It allows us to define a metric. All of this is the same, but now this covariant operator is, of course, not the flat operator anymore, but it is the unique derivative operator on M such that for all time-like curves on M with four velocity fields psi, this is equivalent. So basically, the right-hand side would be the tangent vector of a curve would follow the geodesic equation, but of course, with a given force, the gravitational force, which is the right part of the equal sign, is basically would be saying like so mass plus acceleration is equal to the gravitational force, which in manner taking into account that the mass of gravitational mass and inertial mass is the same. So this formulation there is just exactly equivalent as a geodesic, assuming that this covariant operator has included the interaction. So we have geometrized away gravity, introducing this new geometrical structure, affine connection with the G, okay? And then from that, we can actually compute the curvatures associated to this covariant derivative operator, sorry. And then we get these equations there, which is basically just a very similar touch of what would be the Einstein's equations, okay? But of course, not relativistic, but relativistic here in the sense that it's not Lorentz invariant, of course. We will come for that tomorrow and Thursday, but it has this similar structure in terms of geometry of space-time, okay? So let me finish here by at least have convinced you partially that Newton mechanics can be formulated in a coordinated independent manner with this geometrical structure. That's one thing. Second thing, I didn't write there, but we are talking about space-time, so there's nothing strange about talking about space-time in Newton mechanics, just as special relativity or GR. Third of all, which is even worse, where gravity manifests itself as curved space-time, okay, in the four-dimensional space. So these three facts that we usually associated with GR are already present in Newton space-time. So I want to finish here by saying that these ideas are nothing special to GR, okay? And especially the coordinate independent description of this geometries, this space-time, What is something that people will think when they're talking about GR being covariant. It's a special thing. But here we have already a covariant way of defining Newton mechanics. And I will go on Thursday probably to exactly be precise on this, what we define about covariancy here, because obviously Newton's mechanics still have some underlying symmetries, the inertial systems, the inertial frames. So our language is equivalent to the usual formulation of Newton mechanics, which has some underlying symmetries, the Galilean transformations. So there is something special about this, but one has to be very precise in what we define about covariancy in terms of writing laws independent of coordinates, because this definition is not special to GR, okay? So I think I will finish here. If there are questions, we have some time for answers.
Well, thank you, Antonio. That was an incredibly provocative second half of your lecture. So remember, for all the participants, this is a school, so you're encouraged to ask questions, and especially after this, I'm sure you're certainly looking forward to the next chapters of this course, but there's now a chance to ask Antonio more questions.
Yeah, I'm sorry if I took too much time on introducing Newton's theory, but I really want to try to understand that the concepts usually we connect with GR are intrinsic in our theories. So tomorrow we will see more about special relativity. Of course, you are already very familiarized with the geometrical formulation of special relativity, so it's not so provoking to do it. We will go very quickly to do that. But then I want to compare special relativity with Newton's theory to see what's really the difference, apart from the physical idea of that. Of course, we explain propagation of light in a good manner, but really, what is the geometry difference between each other? And then on Thursday, I will talk about GR. But I hope at least I did make clear that the geometrical concepts that we introduce in for space-time can be not only the metric structure that we are familiarized with, but actually we can say more, and we can even think about if physical laws give us on our hand the geometrical notions or do we impose them before, and there we can really discuss about how is that, because of course what we are learning in physics is more about matter, how matter behaves and so on. And then one can ask if the different experiments we do with matter will prescribe us some space-time structure or not, or should we always think about space-time structure before? Of course, this is the whole, in my opinion, the whole trick about quantum gravity, right? Because this is the special thing about gravity in terms of space-time, and then one really have to think about what comes first, if matter or space-time or so on and so forth. But that's, hopefully I can at least make you a glimpse of what this is about.
Fantastic. So we have a raised hand by Caroline. So
Sorry, yeah,
question.
okay, yeah.
Thank you. It was an amazing lecture. So one is basically more of a comment, if you could comment on top of that, and the other one is a practical question. So in terms of I don't know if you can put it like this, but in terms of the ontology of space-time, this thing that I think it's really nice when you can see that this structure is somehow retained in all of the theories from Newton to special relativity and GR, you retain this sort of geometrical approach. So I don't know if you ever thought about this, but what does this like structural retainment tell us about, if you can tell something about the ontology of space-time somehow, if like you can abandon these abstract notions of frames and talk about geometry, what would that imply in terms of our how we construct this physical interpretation of reality? And the second point is when you mentioned just locally, I'm sorry for asking that because I said it's just local, but what would be the differences in the definitions if we are trying to say things globally? And this is like more of a, I don't know if you can, if this is going too off topic. Thank you.
Yeah, so the first question is very interesting. And of course, for philosophers, this has been key in the last century. Now, I think the answer is for me not clear. I would say from the literature you can find two positions. One is maybe more successful of people following it than other, but the geometrical position is one, and you are completely right. It seems to be that geometry is part of our physical laws. Now, there are two things that one can think that maybe this is not the case. One is, okay, one is an authority argument, which is that Einstein really didn't believe that space-time is geometry, which is a bit of a myth that Einstein really thought about geometry. He thought that geometry was not really, there's nothing special about space-time being geometry. It's just that what he thought about geometry is really the motion of bodies. So he really thought about matter. And if matter moves in a non-Euclidean way, then you can say something about geometry. But that's independent of the idea that space-time in itself is geometry. So another position the second idea is that we don't experience geometry if we don't have matter. So then one idea is that maybe geometry can be described in terms of matter. Now, of course, this goes in a very complicated discussion because we know, for example, that we have solutions of general relativity like gravitational waves that do not depend on matter in principle. You can propose them as just being there in the universe. But then, and that's a bit spoiling what I want to say at the end of the lectures, is that actually maybe we can think that the proper metric of the geometry in GR is not, maybe it's not only space-time, but it could only also be matter. And then maybe these definitions of matter in one hand, space-time plus geometry in other hand, this distinction doesn't really make sense even in our new theories. So these are just small arguments about that. It's a very intricate discussion on what are the, let's say, yeah, ontological features, like what ontological features do our theories prescribe? Because one could say, well, actually, as I said, the universal thing that Newton's dynamics, special relativity, and general relativity have in common is the manifold structure. So one position could be, well, maybe it's just the manifold structure actually that is inherent in the nature. And then we just have to prescribe different geometries as we learn about physics. As I say, it's complicated. I think different positions lead you to understand different ideas. And then depending on which ideas you value more, you can have one position or another position. And the second part about the global features, well, I'm not a specialist in relativistic physics too much, so probably this would be a question for other courses, but you can define global notions like asymptotically flat spacetime and so on. So there are global notions in GR that you could define. It's just that in the basic formulations of GR, the Einstein's equations basically, and the geodesic equations, you can define in a local way. I just highlight the locality because in Newton's spacetime, there are more notions of global notions that in GR because of the structure of spacetime. And I was only trying to say that we don't need that. So the thing that Newton spacetime is has some global features. You can still define Newton's physics without that, and you can still define local, the same as you would do in GR, only defining concepts that are defined on a point in a neighborhood and not globally, as for example, the notion of a distance, right? When you have a distance that connects 2 points, usually do that in Euclidean geometry. Then you say, oh, the distance divided by the time is the velocity. These notions are global defined, but so they are not local. We don't need them. Okay, we can define Newton mechanics without that. So that's what I mean by definition of locality. So that nobody tells me, oh, because Newton is global. No, you don't need that. Okay. That is what I was trying to refer to. But then in GR, you can define global features sometimes, but they're on top of our description. Hope that answers the question.
Yes, it does. Thank you very much.
If there is no other question, I may have to leave.
Oh, that's okay. So we reconvene tomorrow for the next lectures, and and there are other courses happening later today, so you're free to join. You have the Zoom links. So yeah, thanks everyone for joining, and see you
Thank you.
tomorrow.
See you tomorrow.